Hello, good day to all. Today we'll be covering the measurement techniques and uncertainties from the A-level physics syllabus. This is part of the AS portion, and I hope you all understand. So for every reading, there is an uncertainty. So for example, this line, which is 10 centimeters, let's write that down, 10 centimeters, has an uncertainty because of the scale that is used to, or any instrument that is used to measure its length. So for example, for a scale, the least count is 0.1 centimeters or 1 millimeters. And in general, the uncertainty of an instrument is half the least count. So for a scale, it would be half its least count, which is half into 0.1 centimeters. Let's write that down. That is the formula. And so it's half the least count, which is half into 0.1, which is 0.05 for the scale. And when measuring between like lines or anything at all, it is the uncertainty of the instrument times the number of points the length is being taken or being measured across. So for example, for this line, it's between 2 points, so it's 0.05, or the least count of the instrument, times the number of points, and the number of points here being 1 and 2. So 0.05 times 2, which is 0.1. And we express the magnitude as 10 plus or minus the uncertainty. Now there's three ways to represent an uncertainty. And let's just take this as an example. 10 plus or minus 0.1. The first way is the absolute uncertainty, which is the value itself, so 0.1. The second way is a fraction uncertainty, which is the absolute uncertainty divided by the magnitude. So over here it's 0.1 divided by 10. Let's write that down, which is 0.01. And the third and the most common way to represent it is by percentage uncertainty, which is the fraction uncertainty times 100. I'm pretty sure you all know how to convert fraction to percentage. So let's just write that down. So to recap, there's three ways to express an uncertainty. The first way is absolute, AB. The second way is fractional, and the third way is percentage. Now, most of the problems in our syllabus require us to combine uncertainties, and there's multiple ways to combine an uncertainty. In fact, there's three. Again, and the first way is, let's take for example a formula, x is equal to PR. It's not an actual formula, but let's just assume it is. And so let's give P and R a value. The first way is when you have to add. Let's say the formula is P plus R and you have to add or subtract. What you do is you have to add the absolute uncertainties. Add AB. So for example, over here it's P plus R. So to add, you would have P plus R, which is 1 plus 2, which is 3, plus or minus adding the absolute uncertainties. So 0.2 plus 0.1, which is 0.3. The second way is when the quantities are being multiplied or divided. In this case, you multiply the quantities and you add the absolute uncertainties of the quantities. So for example, in this case, P into R, so P into R, which is 1 into 2, which is 2. Plus or minus, over here, you would have to add the percentage uncertainties. So the percentage uncertainty of P plus the percentage uncertainty of R. Which would give, I suppose, 20%. And the last one is when it's not being multiplied, it's being powered to a factor. So for example, x is equal to p square. In this case, you multiply the percentage uncertainty with the factor that is being powered, raised to power. So for example, p is 1, so p square would be 1, and the percentage uncertainty of p is 10%. So 10 times the power, so 10 times 2, which would give you a 20% uncertainty. Now let's try and do a question. So the current is 2.5 plus or minus 0.05 milliamps, and the resistance is 4.7 plus or minus 2%. And take that the resistance is in ohms and current is in milliamps. What is the power? Hint, the formula for power is I square R. Or if you want to first find the voltage, you can do that too. Okay, I hope everyone's had an attempt. If you haven't, let's move on with the working. Oh, sorry, it's not milliamps, it's amps. Okay, well, let's assume it's milliamps, okay? And this is also in ohms. So the power would be by the formula I square R. And notice that this is in milliamps and this is in ohms. So you're going to have to convert back to SI units, the standard units. So amperes. I will be amperes. So to convert milliamps to amps, you're going to have to do 2.5 into 10 to the power minus 3. And that is your current value. So the power would be 2.5 10 to the power minus 3 square times the resistance, which is 4.7. And that would be rounded to two significant figures, 9.4 into 10 to the power minus 5 watts. That is not all. You're also going to have to find the percentage, the percentage uncertainty. And that is I square r 0.05, sorry, 0.05 divided by 2.5 times 100, that is 2%. And the other one is, well, by the same method, you will get 2%. Again, the percentage is already given, so it's helping you. So by the previous rule, like the ways to combine uncertainties, we have learned that if there is a power, we multiply, and when they're being multiplied or added, sorry, multiplied or divided, we add the percentage uncertainties. So I square r, I is being first squared and then is being multiplied to r. So the percentage uncertainty would be 2 times the power 2 plus the percentage uncertainty of r, which is 2, is equal to 2 into 2, 4 plus 6%. So you can say plus or minus 6%. Now often they ask you to express this as an absolute uncertainty. What you can do is, so this is the value of the magnitude, so something divided by this value times 100 gives you 6%. So 0.06 x divided by the magnitude is this, is equal to 0.06. Make x the subject, and that is the absolute uncertainty, which is 1.8 into 10 to the power minus 6. But whenever we're expressing as an absolute uncertainty, we tend to write it in one significant figure. And so this would be 2 into 10 to the power minus 6 to 1 SF. Now moving on to the last part of this lesson, and that is random errors and systematic errors and how to identify. So there's two types of errors when you're taking a reading. There's two. The first one being a random error, and the second one being systematic. A random error usually occurs due to uncertainties of measurements due to the observer. So for example, let's say the observer is not paying attention when doing the experiment. That's when a random error occurs. It is not due to, or not in any way due to the equipment, or faulty equipment. And to identify a random error, it is usually, so let's say you're plotting a graph of x, sorry, this is y against x. A random error can be identified as, when you're drawing a line of best fit, so let's say this is a line of best fit, a scatter across the line of best fit. So how to identify a random error? On a graph, the plot would be scattered, and it is due to the observer. The second type is systematic, sys for short. And to identify systematic errors on a graph, there's no particular way of identifying, there's no particular way of reducing the systematic error. It is a fault. It can be a result of the faulty equipment or changes in the environment. But the way to identify it is, let's say, by a graph of y is equal to mx. The graph is supposed to pass through the origin. However, let's say I'm measuring voltage against current. So let's say a graph which is supposed to pass through the origin doesn't. Let's say it passes like this. Through the graph you can recognize, or you can tell that there's a systematic error in the voltage. Same way to identify whether there's a systematic error in the current or not. In this graph, there's a systematic error with the current because it is intersecting with the x-axis, and over here it's intersecting with the y-axis before the origin, or not the origin. And as mentioned before, there's no clear way to reduce systematic errors. However, there's a way to reduce random errors, and that is to repeat the experiment, take averages, and taking several readings, and this also increases the precision of your experiment. And that is the way to reduce random errors. There's two important definitions also that you have to learn. The first one is accuracy, and the second one is precision. Accuracy is like, let's say something is 10 centimeters and your reading is 9.9. We say that this reading is accurate because it is close to the value of it is close to the actual value. Precision is determined by the precision is determined by the least count, and also determined by how close the values are to each other. So let's say you have 10 centimeters, and when you take readings, you get 9.8, 9.7, 9.8 again, 9.75. That means your values are precise because they are close together, and they're determined by the range of values that you have. And that is all for this lesson. I hope you all understood. If you do have any doubts, please leave it in the comment section.